Section 7.4 for intermediate algebra, rationalizing denominators or numerators with one term. When they ask us to rationalize the denominator, they're asking us to simplify the radical and eliminate having a radical in the denominator. That's what rationalize the denominator means, and it used to be very important that we always rationalize the denominator and eliminated the radical from the denominator for it to be in correct form for a radical. Now with the use of calculators and decimal equivalency, oftentimes this isn't the case, but the skill still needs to be there for an exact answer. When we convert radicals that aren't perfect, squares or cubes, whatever the root happens to be, to a decimal, we have an approximation, and it can affect our answer if we swap out the radicals with a decimal too early on. So let's look at what this means. We have the square root of the quotient 36/5. We can separate this into, using our quotient rule, the square root of 36 over the square root of 5. There was nothing common to simplify ahead of time. Simplifying this, the numerator is a perfect square since 6 to the second power is 36. So the square root of 36 is 6. But the square root of 5, we only have 1 5. This is not a perfect square. And here's where rationalize the denominator comes into play. We don't want to leave our answer with the radical in the denominator. We need another 5 underneath the radical to make this a perfect square. So if we multiply the denominator by the square root of 5 so that we now have square root of 25, multiplying these radicals together, we're going to be able to eliminate the radical. But to maintain equality, we'll multiply the numerator by the square root of 5 as well. Essentially, we're multiplying by 1. Square root of 5 over the square root of 5 is 1, so we're not changing any values. To simplify this then, we have 6 times the square root of 5. The 6 isn't underneath the radical, so it'll stay in front. Here we have the square root of 5 times the square root of 5. That is the square root of 5 times 5, and we have our pair. Just as we planned it, this simplifies to the integer 5. The radical is gone from the denominator, and our rationalization of the denominator is the following answer: 6 times the square root of 5 over 5. In this next problem, they're asking us to simplify this. Well, underneath the radical, we have a common factor of 2. So if we separate this into the rational integer part, 3/4 times the square root of, we'll put those using our quotient rule for radicals underneath one radical, and simplify from there. We still have our 3/4, but in the meantime, 6 divided by 2 is 3. 2 divided by 2 is 1. We have the square root of 3 in the numerator, and we have the square root of 1, which is 1 in the denominator. There is no radical in the denominator now that we need to worry about rationalizing it, other than writing our answer multiplied together and having that denominator of 1 is understood. So we have 3 times the square root of 3 over 4 times 1, or simply 4, for our final answer. Rationalizing the denominator also works with other indices, and here we have the 4th root of 5/8, which 5 and 8 don't have anything in common, so I'm going to separate this into the 4th root of the numerator over the 4th root of the denominator, and instead of writing 8, I'm going to write the prime factorization of 8. 8 is 2 times 2 times 2. For this to be a perfect 4th root, we would have to have another 2. If there was only one more 2. So how do we put another 2 in there? We're going to put the 4th root of 2 and multiply it by the denominator. But so that we don't change our expression, we want to keep it in equivalent. We also will need to multiply the numerator by the square root or the fourth root of 2 as well. Fourth root of 2 over the fourth root of 2 is equivalent to 1. It doesn't do much for us in the numerator. We have common indices, so we can multiply our radicands together with a radical multiplication, which gives us the fourth root of 5 times 2 or 10. But in the denominator, fourth root of 2 times 2 times 2 times 2, we do have 4 2's, is 2. And we have rationalized the denominator, which means eliminating the radical from the denominator. In this next problem, we have a quotient of radicals, which we can combine, since there is a common factor here underneath the 1 radical. 6y over 12x. We have a common 6. 6 divided by 6 is 1. 12 divided by 6 is 2. Remaining underneath the radical is a 2x in the denominator. To rationalize the denominator, we would need another 2x so that we have 2x to the second power. So I'm going to multiply the denominator by another 2x. If I'm multiplying the denominator by square root of 2x, I'll need to multiply the numerator by 2x. This is our special 1 that we're multiplying by. In the numerator, we have the square root of 1 times y times square root of 2x. We can multiply those together underneath 1 radical. Y times 2x is 2xy. In the denominator, we had our reduced 2x, and now we're multiplying it by the square root of another 2x. We have a pair of 2's, we have a pair of x's. Square root of 4x squared is a 2x. So our final answer, with a rationalized denominator, which means the radical is gone from the denominator, is the square root of 2xy, that quantity, over 2x. There are occasions when it is necessary for us to rationalize the numerator, which means now we're concerned about getting the radical out of the numerator. So let's take a look at a couple examples here. Square root of 7/2, there's nothing common, so we will break this into an equivalent expression of square root of 7 over the square root of 2. And this time our focus is to eliminate the radical in the numerator. We have 7 to the first power. We want to get rid of that 7 to the first power. We need a perfect square. That would require us to have another 7 underneath the radical. If we're multiplying the denominator by square root of 7, we need to multiply, or the numerator by square root of 7, we need to multiply the denominator by square root of 7. Square root of 7 over square root of 7 is 1. But this special one now allows us to take this a step further. Square root of 7 times square root of 7 is the square root of 7 to the second power, or square root of 49, which is 7. We have our pair of 2's that we're taking the square root of. In the denominator, when you have radicals multiplied together, you can multiply the radicands. 2 times 7 is 14. There is only one 2, there is only one 7. We can't simplify that. And we have rationalized the numerator, which means we've eliminated the radical from the numerator. In this next problem, the instructions are still to rationalize the numerator with it as well. There's nothing common in this quotient, so let's separate it into the 2 radicals. The square root of the numerator, m to the third n, over the square root of 3. We can simplify this. Square root of m to the third is a higher power underneath the radical than our index. That means we have 3 divided by the square root, or 2 power. 3 divided by 2 is 3/2, which is 1 m out and 1 m left over. We have a pair of m's and one m left over, and we have our n over the square root of 3. We'd be done except for the instructions that tell us to rationalize the numerator. We want to eliminate this radical. We have an m to the first and an n to the first. We need another m and another n to make pairs for each one of those. And if we're multiplying the numerator by the square root of mn, we need to multiply the denominator by the square root of mn as well. Simplifying this, we now have a pair of m's and a pair of n's, which brings out, here's our original m, brings out an m from the square root of m squared and an n. In the denominator, we have 3 to the first, m to the first, n to the first, all multiplied together underneath one radical. There is no higher power than to the first in each one of them. And our final answer, instead of m times m, we could write this as m to the second power n over the square root of 3mn for our simplification and rationalization of the numerator.